Until now, we have considered individual devices or components of a power system, which include generators, transmission lines, and transformers. While it is possible to have an isolated generator feeding an isolated load, the move ever since power systems were invented, the move has been to actually to make larger grids where a large number of loads and generators are kind of pooled together, and power is transmitted using transmission lines. So you have a kind of a grid. In fact, the grid is essentially a transmission network, and at various places you have got generators injecting power and loads drawing power at other buses. Now, why should we have grids instead of isolated generators feeding isolated loads? The two reasons are, of course, economy and reliability. Economy, because often you will find that it is cheaper to generate electricity at certain places, and for example, if it is a hydro generator, obviously it makes sense to make a hydro generator near some water resource. And also economies of scale may dictate that you have larger generators rather than many small generators. Of course, this economy of scale is now being challenged by modular power generation systems like solar, etc. But at least about a couple of decades back, it was understood that larger power plants near where the resources are were in fact cheaper than many smaller power plants. Eventually, we are coming around to the view that you can in fact have the economies of scale may not hold, because smaller modular units near the loads also may eventually turn out to be an economical proposition. But as far as large power plants go, they usually will be here where the resources are located. Now, since you have got if you have got larger power plants, you can in fact feed larger number of loads. You in fact, so it makes more sense to have this kind of setup where various generators pool in their generation into a transmission grid, and the loads kind of extracted at other places. You will find that and when you have got these bulk power transmission, it is technologically feasible to transmit power over large distances via a high voltage transmission grid. Also, if you look at it from the point of reliability, you will find that since you got a large number of components connected to a power grid, what you find is that the failure of one or two of the components, one still may be able to ride through such failures. For example, if you got a mesh transmission grids, the loss of a transmission line can be compensated, because the other transmission lines could take out, which are connected in parallel, could in fact continue to handle a slightly larger power flow. So, reliability is a major aspect. If you have got a single generator feeding a single load, if the generator fails, the load essentially the load cannot be catered to. But in a large power grid, in fact, the other generators can in fact incrementally change their power and feed an additional load. So, even though one generating station or a generator is out. So, there is some advantage of having a large number of transmission lines and a large number of generators which are pooling the power, and loads are pulling it out at various places, rather than just having a large number of isolated generators and loads. Okay. So, of course, the scale at which how big you want a grid is something which again is dictated by these factors. A larger grid is usually provides you additional reliability. A very small grid, you have the same problem of fewer number of components, and the failure of components is likely to have more of an impact. Now, however, because a large number of small modular generating systems have now come into practice, like solar power generators, small wind generators. One of the important things is that people especially in remote regions may in fact operate a smaller grid, which is again may be connected to the major bulk power grid, but it could also operate like a small island. So, you can actually the scale of the grid could be small, and the transmission of power could be taking place at lower voltages as well. Such systems are called microgrids, where you have got a set of smaller generators at a lower voltage grid feeding a small number of loads, and this makes a lot of sense in case your system is isolated. But connecting to a large bulk power grid often gives you a large amount, a greater amount of reliability. So, the move has been to in fact have larger number of interconnections, larger number of grids. In fact, today you have intercontinental grids, I mean in the sense that you have got large number of countries which are interconnected to each other, and they exchange power through various means, through transmission lines, AC or DC transmission lines. So, this is what this economy and reliability effectively meant that people preferred to have a large number of things connected to each other, and that is basically the meaning of a power grid or a power system. The typical bulk power system usually will consist of several generators connected to each other. Remember that once you start interconnecting various components together to form a grid, there is a kind of a need for standardization of voltages and frequency. Now, of course, depending on the technological development at a given time, the highest voltage level may be restricted. I mean, to say for example, right now most of the high voltage lines in India are restricted to 765 kV, but before that we had 400 kV, 200 kV and so on. So, as you go for higher and higher voltage levels, of course, you can transmit more power, but you need to overlay this for example 765 kV grid over the 400 kV grid, which is again overlaid over the 200 kV grid. So, actually you need transformers to actually connect all these sets, layers of voltages which are there in the system. So, of course, when you connect each other, there should be standardization of voltages so that people can mass produce equipment, and you do not have to custom build equipment for every application. So, in some ways the voltages, and in fact for the same reason the frequencies are in fact standardized. Okay. So, for example, in India the frequency for AC transmission is of course 50 hertz, and there are several voltage levels. Generally synchronous generators would be generating at large synchronous generators could be generating at voltage voltage which would be 15 kV. 15 kV of course refers to the line to line RMS voltage. It is a 3-phase system, and these are usually stepped up, and you have transmission at 220 kV or 400 kilovolts, and of course since the high voltage levels, although they are high voltage level 220 and 400 kV have got a roughly a ratio nearly about 2. So, it is more economical to in fact have connections using auto transformers rather than a complete two winding transformer. So, auto transformers in fact are more economical than typical 2-winding transformers, because of the fact that for lower turns, for lower transformation ratios, in fact there is a economic advantage. Now, one of the important aspects here is of a bulk power system is as compared to a lower voltage grid is that usually at the bulk level, the larger power system, transmission lines are meshed. That ensures a great deal of reliability. Another thing is that although loads themselves could have a little bit of unbalance, they could be single phase loads, etc. Once you aggregate loads in the distribution system, by the time you reach the transmission system, when you look downstream, more or less the loads are balanced because of a large amount of averaging which takes place. So, the bulk power system, the high voltage grid is mostly a 3-phased balanced system, and it is a meshed system, that is, there are parallel paths in transmission, AC transmission or DC transmission, the parallel paths which are present, and also more or less a balanced system. So, this is one of the key aspects which you will see when you go to when you make a large power grid, okay, that more or less it is balanced at the EHV level, extra high voltage level. At a distribution level, you have in fact more and more radial systems, that is, at the absolutely downstream, usually your system is radial, that is, a load is fed from one distribution path or distribution line, it is not fed from 2 or 3 distribution lines. This is because it's much easier to protect such a system. It's easier in the sense that it's easier to isolate where the fault is in case there is a fault in the distribution system. So, distribution systems are generally radial. Of course, there can be parallel paths which are normally open, in the sense that in case one the line which normally feeds a load is having a fault in one section, you could in fact have another path, but that is normally kept open. So, some distribution systems in fact have such a system, but normally when you are operating in a distribution system, usually you have got radial feed to the load. Radial means that there is no other parallel path, no other transmission path to the load. Okay. But in event of some disturbance, you could of course switch over to another path which is normally open. Okay. So, this is what we normally see in a distribution system, but things could change, and eventually we could have in the future a meshed distribution system as well, although so far it has been more convenient from a protection perspective to isolate and locate faults, to have in fact a radial system. On the other hand, a transmission system is meshed, as I mentioned. So, a fault on a transmission, one major transmission path does not totally interrupt the power flow. Usually, you have some parallel paths connected as well. So, of course, within a bulk power system, you could have a few DC links. The DC links could be embedded within the AC system, or you could have DC links as the only path between two regions, and that of course slightly changes how the system is operated, as we shall see later. The transmission lines, long distance transmission lines is of course carried out using high voltage transmission lines, high or extra high voltage transmission lines. Yeah. Now, we focus our attention now to the nature of power grids. There are two kinds of power grids. One is known as synchronous grids. Synchronous grids are essentially synchronous machines or synchronous sources which are interconnected by AC transmission lines. Now, one fact which we have learnt before is that in steady state, the power flow in AC lines is a function of the phase angle difference between the voltage at both ends. In fact, for a lossless line with a series reactance of X, you know that the voltage, the power flow is V1, V2 sine delta 1 minus delta 2 by X. So, in fact, the power flow in a transmission line is also related to the relative rotor position in the synchronous machine. So, now there is a relationship between a mechanical variable, that is a relative rotor position in synchronous machines, and the voltage phase angular difference which appears across transmission lines. And this aspect we will quickly, through a simple example, try to illustrate to you. Now, one of the consequences of all this is that the frequency normally the frequency throughout a synchronous grid is the same in steady state. So, in steady state, if you are operating stably, the only acceptable operation is when the frequency throughout the synchronous grid is the same. If it is not the same, we shall see what happens. Okay. So, it is important that the frequency remains the same throughout the grid in the steady state. Now, the thing is that of course, there are transients, but after the transients is died down, all the synchronous machines are running at the same electrical speed, okay, or in fact the frequency everywhere is the same. Now, that is the only acceptable mode, because if you do not have frequencies equal, then the power flows etc. are not steady, and this is something we shall try to understand in the next few slides. The other kind of systems which you have are what are known as asynchronously connected systems. Essentially, you can have asynchronously connected systems through DC links, where you convert the AC on one side to DC and then again convert it to AC using converters. Usually these involve power electronic converters, and in asynchronously connected systems, usually power flow is regulated between the two systems and 2 or 3 systems, and the frequency in each individual system need not be the same. What I meant really was that the frequencies of 2 different grids which are connected by an asynchronous grid need not be the same. So, you can have a 50 hertz grid connected to a 60 hertz grid via a asynchronous grid, or you could have 2 systems whose nominal frequency is 50 hertz, but they could be operating at slightly, one could be at 49 or the other one could be at 51. This is an acceptable kind of situation in asynchronously connected systems, okay, but cannot be tolerated in synchronous grids. Now, of course, we need to understand synchronous grids in a little bit more detail. So, I will just give you some simple examples to illustrate the whole concept of synchronous grids and what kind of phenomena you can expect in synchronous grids. So, synchronous grids, the most common manifestation is having synchronous machines connected to each other using AC lines. Okay. So, first of all, of course, what I am saying here about synchronous machines could well be applicable to other synchronous sources, like for example, inverters connected to each other. These also are like a synchronous sources. So, if you have got synchronous machines, as we know, a synchronous machine is essentially has on its rotor an electromagnet, and that rotates, and because it rotates, it causes voltage on the stator winding. It is not shown here very clearly, but there is a stator winding. I have just denoted it by V1 here, and there is of course a winding here, and of course this does not look like a winding, but essentially it is a winding here, and voltage appears across this V1 because it sees a rotating flux. So, this rotating flux, because this rotor is rotating, you will see a voltage which is sinusoidal. So, you will find that usually the design of the machine is done, the air gap as well as the winding design is done in such a way that you get more or less sinusoidal voltages. So, if you have got a winding of a certain phase which is wound on the stator and sees this rotating flux, you will see a sinusoidal voltage appearing across it. Essentially, you have got this rotor which is this is the field winding and it is rotating, and in fact, you have got the voltage V1 which is kind of seen on the stator winding. So, this is what I really want to show, and somehow that winding did not come out well in the diagram which I have shown you here. Now, in case you have got these 2 machines, synchronous machines, one is both the machines say are rotating at the same frequency. Okay. Now, so what I mean is that the electromagnets here and here are rotating, electromagnet here and here is rotating exactly at the same electrical speed. Remember, the pole numbers could be different, but the electrical speed is the same. Now, the thing is that if you have got windings V1 and V2 aligned in the same way, and these 2 electromagnets are moving at the same speed, but if I take a snapshot at say t is equal to 0, what if I notice that this magnet is slightly lagging this other magnet. The speeds are the same, but if you take a snapshot, one of the magnets is aligned at a slightly different position. So, if I just take a say a snapshot of this and I see it like this, then the voltage V2 it turns out will also be slightly different. The voltage which appears across V2 will be in fact lagging the voltage across V1, because both the machines are running at the same frequency of course, but the position of the electromagnets is different. So, whatever happens to V1 happens to V2 a bit later. So, that is why there is a phase lag between V1 and V2. So, you have got in fact a kind of a phase lag between these voltages. The important thing which I wanted to discuss with you here is essentially the position, the mechanical position in the sense which I am saying. If you take a snapshot, there is a mechanical a slightly difference in alignment of these two electromagnets that manifests as a phase difference in the voltage. So, if you take these two machines, their voltages would be having a phase difference. Now, let us also look at another fact in sinusoidal steady state. If you have sinusoidal steady state or you have got almost sinusoidal steady state, the power flow in the transmission line here is in fact a function of the phase angular difference. So, if you look at the phase angular difference, the power flow is proportional to sine delta 1 minus delta 2, okay, for a lossless line. So, if you take a 3-phase transmission line, you will find that in fact the voltages, if the two voltages are, there is a phase angular difference, there will be in fact a power flow through the line, okay. Now, one of the points which you should keep in mind here is that this power flow is not proportional to delta 1 minus delta 2, it is proportional to sine of delta 1 minus delta 2, and sine of delta 1 minus delta 2 is actually not a linear function in delta 1 minus delta 2. Okay. So, it is not that if I increase delta 1 minus delta 2, power flow will proportionately increase, it will not proportionally increase, it will increase proportion to sine delta 1 minus delta 2. Okay. And of course, the power flow is dependent on this reactance x. In fact, it is for the simple lossless system, it will be V1 V2 sine delta 1 minus delta 2 by x. Okay. But this variation is non-linear with respect to delta 1 minus delta 2, that is one important point. Now, when you put these two facts together, now what are the facts we have considered? One, the phase angle of the voltage which appears at the terminal of the machine under open circuit conditions is dependent on the rotor angular position. So, the rotor angular difference in fact manifests or is evident as a voltage phase angular difference. And the second point is that the voltage phase angular difference will in fact determine the power. Okay. Of course, one small point here is that what I have shown here is I mentioned before is the open circuit voltage. When you actually load the machine, this is not strictly speaking true. The voltage V1 and V2 will be dependent of course on this difference of rotor positions, but it will not be, the phase angular difference will not be equal to the rotor position, difference of the rotor position. But keeping aside this small point aside, I mean it is a significant point, but we will just keep this aside. What you need to take away is the phase angular difference between V1 and V2 is dependent on the rotor positions. Okay. So, this is fact number 1, and fact number 2 is the power flow is dependent on the phase angular difference. Now, if you put these 2 and 2 together, if you have these two synchronous machines connected to each other by a transmission line, what do you see the picture? The electrical power which flows which is dependent on the load power as well as the flow of power in the transmission line will dependent on the phase angular difference. Okay. The mechanical power is of course driving the electromagnet or the rotor. The electrical power is in fact, since this is a generator, it is a retarding kind of it is causing a retarding torque. So, what we we see in fact power is almost proportional to torque, that is because normally you would be operating near 50 hertz. So, what we will see here is a very interesting thing is that the system tends to stay in synchronism. What do I mean by this? That is, if this synchronous machine here suddenly, suppose this is all in steady state and this suddenly accelerates. Normally in steady state mechanical power and electrical power for both machines is mechanical power is equal to electrical power for this machine, as well as the mechanical input power for this machine is equal to its electrical power output. So, there is a generation load balance overall as well as in the individual machines. Okay. So, the individual machines mechanical and electrical power is in fact going to be equal. Now, because these two powers are equal, the machine does not accelerate. Okay. That is the main thing. Now, in case we are in steady state and suppose this machine, because of some disturbance, okay, disturbance means some sudden change in condition, slightly accelerates because of some reason. So, what will happen is this electromagnet will go slightly ahead because of the disturbance. If it goes ahead, what are the kind of things which follow? Because this goes ahead, the phase angle of the voltage here increases, as we have discussed before, because the rotor position determines the phase angular difference. So, since this is accelerated slightly with respect to this, the phase angle of this becomes higher than this, and because that happens, there will be increased power flow through the line. There are many other things which happen, but this is a simplistic picture, but I hope you will be able to using this simple model understand what I am trying to say. So, the power flow in fact increases. Now, if the power flow increases, this power is being fed from here in the transmission line. So, what will happen is that power flow in this direction, there will be increase of power flow in this direction, and therefore, the electrical retarding force on this will increase. So, what happens is that if one of the machine accelerates with respect to the other, then what happens is the electrical power kind of retards it. So, it tries to restore it back to its original position. So, in fact, the electrical transmission network tries to ensure that the rotor positions, the speeds of the two machines in fact remain the same. In fact, if one of them tries to increase, the flow, the angle increases here, the power flow increases. Because the power flow increases, this retards. So, any machine which tries to slightly increase its speed will find that it is facing a little bit more of retarding force. So, there is a kind of restorative action which occurs and which keeps the machine in fact at the same speed. So, in fact, in synchronous grids where there are synchronous machines connected by AC lines, you will find in fact that the interconnected synchronous machines stay in synchronism. You do not have to do anything very special to do that. So, but the important thing is they are connected by AC transmission lines. So, this is one way of looking at this. This is a very simplistic analogy, but is an analogy nonetheless. Of this system is essentially this way. This is the mechanical power which is trying to push the rotor onto one, trying to accelerate the rotor on this in this direction. The load or the electrical power, the load on the machine here is an electrical load. It is trying to pull this mass back, okay, and this spring here also is in fact the force stretch of the spring depends on x1 minus x2. So, if this one mass accelerates in this direction, the spring will compress and it will push it back, okay. So, there is a kind of the two masses try to stay together. So, this is what we call is the machines try to stay in synchronism, okay. So, you do not have to do anything special for this. The inherent property of the transmission network to provide a restorative torque whenever there is a displacement from equilibrium ensures that the masses stay in equilibrium. So, a synchronous grid we had mentioned some time back that the frequency throughout a synchronous grid is the same in steady state. Why is it? Because of the reasons which I have just mentioned some time back. So, synchronous machines connected by AC lines tend to stay in synchronism. They tend to stay in synchronism. This kind of synchronism lasts provided this spring does not lose its stretch, does not lose its stiffness. So, if your spring is of course very weak, you are likely to have more displacements, but you will still stay in synchronism. But if this spring at any moment loses its stiffness, that is it is not able to pull back or it breaks, then the two masses can kind of lose they fly apart and they lose synchronism. In fact, the machines will lose synchronism. So, the fact that all synchronous machines stay in synchronism, in fact, is contingent upon the fact that the transmission lines provide this restorative torque. Now, one of the key points is that, is there a restorative torque? Yes, normally there is, because we find that in a transmission system, 3-phase power is proportional to sine delta 1 minus delta 2. So, what we have is that if delta 1 minus delta 2 increases, you will find that sine delta 1 minus delta 2 also increases. But this is true only for delta 1 minus delta 2 less than 90 degrees. After that, when delta 1 minus delta 2 increases, you will find in fact that the power starts reducing and may even become negative in case delta 1 minus delta 2 becomes greater than 180 degrees. So, the important thing which one has to remember is that this stretch of the spring provides a restorative torque only if your stretch is not too much. So, if because of some disturbance the spring stretches too much, the restorative torque, which is proportional to sine delta 1 minus delta 2, will in fact become can become negative or reduce, and that really in such a situation the generators may in fact not stay together. Okay. So, normally synchronous grids remain in synchronism because the inherent dynamics of this, the inherent physics of this system. Okay. Now, of course, one or two points which you would have noticed, this kind of model is very simplistic. For example, we are talking, since we are talking of stretches and acceleration of the masses, etc., we are obviously talking of some kind of dynamics which is occurring. And so, some of you may wonder that if you are talking of dynamics, why are we using a sinusoidal steady state formula for power flow? We should in fact write down the differential equations of all the inductors and capacitors. L di by dt is equal to the voltage across the inductor and so on. But it turns out that this acceleration of the rotors is relatively slow process. It happens slowly. So, it is a good idea, I mean a good modeling approximation to assume that the transmission network is more or less at its steady state. I mean it is more or less in sinusoidal steady state. So, that so that is the reason we can represent a transmission line simply by and kind of algebraic the power flow versus delta 1 minus delta 2 characteristic, we can take the sinusoidal steady state expression, because the dynamics here are relatively slow. Now, if you in fact we will just extend this further. One of the interesting things is that okay, there is a restorative force, but what is the nature of the transient in case there is a disturbance? One of the interesting things you will see is that if I give a disturbance to this system, you will find in fact that there is an oscillation, provided the spring is provided that the stretch of the spring is not too much. If the stretch of the spring is not too much, remember that power flow is proportional to sine delta 1 minus delta 2, which is positive. I mean, so you have a restorative action. So, if your sine delta 1 minus delta 2 is still positive, you will find that effectively it is like a spring with some stiffness which tends to pull the masses together. So, if you give a disturbance, there is usually a oscillation, and this oscillation is called a swing. So, swings are very characteristic phenomena of synchronous grids. There is also another important thing to be considered when synchronous machines are operating together, is that if the cumulative load and generation is unbalanced, that is PM1 plus PM2 is for example greater than P load 1 minus P load 2. Okay. So, that is the total external forces, the total generation and the total load. If they are unbalanced, in that case the entire the center of mass of the system moves. So, in fact, in this case it will move towards the right if PM1 plus PM2 is greater than P load 1 minus P load 2. So, there are two kinds of motion which are very important. One is the relative motion between the masses, which is in fact oscillatory because of the spring, and the second kind of motion is what is known as the center of inertia motion, what do you call the common motion of the system, and that is in fact dependent on the total load generation balance. So, these are two distinct things. Common motion means both masses move together, relative motion means they of course are kind of swinging against each other. This relative motion is like a spring mass system, like in a spring mass system, but remember again that this spring is non-linear, the stretch of the spring. So, if the restorative forces are proportional to the sign of the stretch of the springs. Okay. So, that is one important thing which you should remember. Now, these are two distinct kind of things which are seen in a synchronous grid. In fact, if you try to go for a larger number of masses, what you notice is that there could be in fact many swing, what you could have is many what you call distinct patterns which you will see. One of the patterns is as before the motion of the center of inertia, and that depends in fact totally on the load generation balance, the total load generation balance. If the total load generation balance is different, if it is non-zero, the sum of the external forces is non-zero, that is Fg1 plus Fg2 plus Fg3 is in fact greater than FL1 plus FL2 and F plus FL3, you will find that the center of motion, inertia motion is there. Now, or in fact if it is less, that is the generation is less than the load, you will have center of inertia motion, but in the opposite direction. So, that can happen. You also have in fact a kind of swing, because if there is any disturbance, then the rotors of course tend to oscillate with respect to each other, and this is again seen in this two mass spring system. So, of course, the important thing or the important difference between a two machines system and three machine system is that now there could be many patterns of relative motion. For example, you would find sometimes that if you have got a large mass and two small masses connected by a stiff spring and this is a weak spring, you can have these two masses swinging together with respect to this mass, and you could also have these two masses swinging against each other. So, you can have various patterns. Okay. In fact, if you have got a three machine system, there are two distinct patterns of relative motion. These are called the modes or oscillatory modes of the system, and each mode is kind of characterized by a specific mode shape or pattern, and it also has a specific frequency, and this frequency depends on the masses as well as the parameters of this spring. So, when you have a multi-machine system, if you have an n machine system, you got n modes of relative motion, and something which will once we see a few real life measurements, I think it will become clear. And you also have the center of inertia motion. So, synchronous grids have got this specific pattern. Okay. Now, so if one tries to look at the nature of synchronous grids, the behavior of synchronous grids very specifically, suppose I plot, suppose I have got a large number of generators connected to each other via AC transmission grid, that is you have got AC links between the generators. In that case, you will find that if there is a sudden load throw off and I plot the generator speeds, you will find that the center of the common motion or the center of inertia motion is seen, because now there is a there is a load generation mismatch. So, if you are initially at equilibrium and you trip a generator, you trip a load, in that case, or when I say trip I mean disconnect a load, you will find that the there is a load generation imbalance, and because of that the total generation is more than the total load, and therefore, the entire system or the center of inertia moves. And of course, this will go on moving, but usually because of governor action, that is because of the fact that the mechanical input to individual generators is in fact controlled using governors, and also various loads like fans etc., the power they in fact they demand or they absorb from the grid increases if the frequency increases. So, there are certain loads which are frequency dependent. So, because of that, you usually at as the frequency deviates from the initial value, you will find that the load slightly increase and the mechanical power to the generator slightly reduces. Okay, that is because of governor action and load frequency dependence of loads. So, what happens is eventually equilibrium is reached, but at a different frequency. Okay. If you have got on the other hand a generation trip, sudden generation trip, you will see a kind of the frequency kind of drops down and an equilibrium is reached because of governor action again and the load frequency dependence of loads. Now, the thing is that of course, if you give a asymmetrical disturbance, you will also see oscillations in the frequency, the what I called as relative motion or swings, which are also seen. If in case you have got a large disturbance, okay, for example, because of some reason one of these masses is say kicked by somebody and it suddenly acquires a very large because there is an impulsive force because of a kick, the mass suddenly acquires a large velocity, it may actually get pulled in this direction. If I give it a kick in this direction, it gets a sudden impulse which pushes it in this direction. Now, that will cause a stretch in the spring. Now, if it is a linear spring, the restorative force becomes proportional to the stretch of the spring, but in case it is a nonlinear spring like actually in a power system where the electrical power is proportional to delta 1 minus delta 2, sine of delta 1 minus delta 2. As the stretch increases, a point comes after which the spring loses its restorative force, that is sine delta 1 minus delta 2 in fact becomes negative, and you will find that the mass is no longer able to come back. So, in such a situation you do not have oscillatory motion, but in fact because of a large disturbance you may find that some generator may actually lose synchronism. In fact, it is an unstable situation. Okay. Another aspect which we see in realistic power grids is that for smaller disturbances you will find that when the stretch of the spring is not too much, you will find that the motion is oscillatory, but sometimes this is not the entire story, because while the machines are oscillating, you will find that various other parameters in the system also oscillate. For example, the terminal voltage of a generator will also oscillate, because now the speed of the machine is changing. Okay. So, the rate of change of flux also changes. So, you find the terminal voltage magnitude also changes. Now, this may, for example, in an automatic voltage regulator, this change of voltage will be picked up by the automatic voltage regulator, and it will start changing because its automatic voltage regulator changes the field voltage of the generator. You will find that in fact the field flux also will start oscillating, and because of that the torque also will oscillate, and suppose this torque oscillation is such that it actually enhances the oscillation. So, because this feedback control system at certain frequencies you may in fact have the oscillation, damping of the oscillation, in fact not dying out, in fact it may feed into or enhance the oscillation. So, this kind of incidentally control systems in the power system can actually destabilize these power swings, and instead of dying out they may be poorly damped or even increase in magnitude. So, these kind of phenomena are the ones at the bottom are in fact situations where the relative motion is not stable, it is called angular instability. Okay. If you look at this motion at the top, you will find relative motion between generator speeds, various generator speeds, but the main motion is in fact the common motion or the center of inertia motion. So, remember of course, before we forget that this is the plot of the generator speeds in a synchronous grid, that is a situation where generators are connected to each other by AC lines. Okay. Now, remember a few points. A single machine connected to a load, synchronous machine connected to a load in this system there is no question of relative motion between generators because there is only one generator. In such a situation, all you have to worry is about the frequency of this generator itself or the center of inertia frequency. The center of inertia frequency in this case is just the frequency of this generator, which is dependent on the load generation balance. And the other it is like having a mass with a load acting in this direction and the driving force, that the mechanical power from the prime mover in this direction and the load in this direction. So, the motion of this mass just depends on the difference between the two. So, you need a governor to stabilize the common motion. This is true even for a multi-machine system. If you have got a machine which is connected to a very large generator or a stiff or a voltage source, a synchronous 50 hertz voltage source, then in such a situation because this source maintains the frequency at 50 hertz, there is no common motion. That is, the generator stays at 50 hertz if it is stable. Okay. However, there could be motion between relative motion between the generator voltage here and the voltage of this infinite bus or the stiff voltage source. So, you can have swing. Swing is nothing but relative motion. Okay. So, this is like having a mass connected via a spring to a very large wall. So, there is no center of inertia motion here, but you can have relative motion between the mass and the wall. Okay. Swing between the mass and the wall. So, this is case number 1, this is case number 2. The third possibility is, so here in this case there is no relative motion, no question of a relative motion. If you in fact have two masses connected to each other, then you have got both common motion and that depends on the total load generation balance, and you also have swing, that is inter-machine oscillation. So, swing is there and common motion is there. The common motion is dependent on the total load generation balance and therefore is can be affected by the load frequency dependence or the load the frequency dependence of loads and governors. These affect the total load generation balance. So, that really, and swings of course are dependent on asymmetrical disturbances given to the system, which could be faults, etc. Okay. The other situation is where you have got a multi-machine system. Here you have got both a swing, you have got several swings, several modes, several frequencies of swings, and you also have common motion. So, this is there. So, these are the 4 situations we should understand in synchronous grids which may be present. Now, remember we are talking of synchronous grids, and a synchronous grid is essentially synchronous machines connected by AC transmission network. Now, interestingly, whatever I have said is not restricted by size, in the sense you could have thousands of machines connected by thousands of miles of transmission lines, maybe a mesh network. But if all the interconnections are, there is at least one AC transmission path between one machine to another machine, in that case you have what is known as a synchronous grid. So, for example, India at present all machines, synchronous machines or power plants are connected by some AC line path. So, for example, synchronous generator say in Trombay in Mumbai is also connected to the grid, and so is another generator say in Arunachal Pradesh. So, you will find in fact the two machines which are interconnected but miles apart, thousands of miles apart, are in fact still running in synchronism. So, that is one of the interesting characteristic of a synchronous grid. Yeah. Now, we would like to see some of these. So now a lot of things you will be able to appreciate if you actually are able to monitor these generator speeds or the frequencies at various places in the grid. Okay. So actually, if you want to really bring you these real life measurements, so that you get a better appreciation, you need actually a measurement system. For example, if I want to show you that the frequencies at various parts in the Indian grid are the same, you would need to actually measure the frequencies at various places, and not only that, you need to time synchronize them, because you need to measure the frequency at the same instant of time. There could be disturbances, and when you have a disturbance, of course, you will find these oscillations, etc. But once you reach a steady state, the frequency is more or less the same. In case there is any load generation balance, you will find that the system frequency will go up and down, the center of inertia frequency will go up and down. So, this is something you can in fact see through what is known as a wide area measurement system if you are looking at a very large grid. Okay. So, we will show you an example of these measurements in a in fact which are being measured even at the current time. These are available in fact through at least at the present time on our there is a website where you can actually frequencies of Mumbai, Kanpur, Hyderabad, Bangalore, all are being measured at present at these 4 locations. These are in fact, all these locations are thousands of kilometers apart. In fact, Mumbai and Kanpur would be say about 1500 kilometers, and Hyderabad, Mumbai, all these are of that order. They are really far apart, but they are actually connected to each other by AC transmission paths. And because of this fact, although they are different locations in the same country, but they are connected, you will find that the frequencies are in fact the same. They are in fact overlapping over one another, and therefore, you can't see them very distinctly, but these are live frequencies. Today is the 4th of December around 10:25, and you see that the frequencies are in fact the same. And these in fact other than, of course, there are a few disturbances which occur, and therefore, the measurement in fact you will find that slightly one frequency could be different from the other, but right now all of them are operating stably. Of course, you will find the frequency going up and down. The reason is, of course, that the load is continually changing. You will find that the load on the system is increasing or decreasing, but the frequency is actually changing in a rather narrow range. Here it is between 50.1 and 49.9. At present, the frequency is roughly above 50 hertz, slightly above 50 hertz. This is the center of inertia frequency. It is just going up and down depending on the loads. The governors in the system in fact are trying to regulate it, may not be exactly to 50 hertz, because there may be a dead band in the governors which prevent operation for very small variations in the frequency. So, this is an example of a measurement which we are taking, and we can in fact see that the system is indeed operating in synchronism. Okay. So, all the frequencies at various locations in the grid are in fact the same. Okay. Now, one of the important things is that although you may think that loads are I switch off a light or a fan in this room here, that will change the load, and that load of course will have some effect on this. If I throw off some load here, the frequency will rise. Okay. But you will find in fact that the frequency, the average effects of many people doing similar actions, some people are switching on loads and switching on off loads. So, in a short time interval, in fact, the aggregate load variation over a certain time interval is more or less almost predictable, in the sense that we know that roughly in the evening in the winter season, what will be the total load. You can't predict it exactly, but you can do a reasonably good forecast of how much load will be there, because when you take an aggregate on an aggregate basis, the load more or less follows a kind of a pattern. Like in Mumbai city, you will find that the load increases in the morning, it will peak because there are a lot of commercial and domestic loads in Mumbai. It will kind of increase very significantly in the daytime, and in the night it will be mostly domestic loads, all the commercial establishments would have closed. So, you will find in fact that there is a predictable pattern of the load because of aggregation. Okay. So, when you go to larger grids, there is a kind of aggregate pattern which emerges, which sometimes can be predicted. I mean, we do have short and long term forecasting algorithms which actually can predict reasonably what kind of loads you can expect at different times of the day, different times of different seasons, different days and so on. Okay. Of course, there could be errors, but using historical data we can often predict what kind of aggregate load will be there. It is very difficult to predict the behavior of an individual load because you could switch off a light here and there, but on the whole the load follows a certain pattern. So, what I am going to talk of here is that one of the interesting things about synchronous grids is that you could have very small synchronous grids, microgrids, or that is AC microgrids, or you could even have very large grids which is continent size. Like for example, India is in fact a synchronous grid. You will find synchronous generators in India are connected to each other via AC transmission paths. Also, most solar generating systems are also grid connected via inverters, which are also synchronous sources to the grid, and these are connected via AC paths, and these are continent sides. In fact, India is also connected to Bangladesh and Nepal and Bhutan. To Bhutan and Nepal, it is through AC transmission lines, and to Bangladesh right now it is through DC lines. You can in fact some of the illustrations I am going to show you here are measurements taken in a wide grid, a big grid like the Indian grid. In fact, it is the Indian grid, and one of the important things when you are taking measurements which are in fact over a wide area is of course time synchronization. You need to ensure that the measurements which are being taken at different places have to be time stamped, so that you can collate them later when you plot them. There is no point in plotting time skewed measurements because they will not tell you how the system is behaving. Also, with today's technology, one can have adequate sampling rate or adequate bandwidth of transmission of data. So, you can in fact transmit much larger amounts of data compared to say a couple of decades back. You can in fact transmit data once in every 20 milliseconds or so to a centralized place where you can in fact store all this information, collate it, use it. In fact, if the delays are not too much, you can in fact use it for even control. So, this is what is known as a wide area measurement system. I thought it is a good time to in fact talk about this right now. Yes. So, I will just give you an example of a wide area measurement system. The one which is a kind of academic one where we use network time protocol based synchronization, and we measure only frequency. So, this is an example. I mean, this is what I am trying to show is here is an example where you measure the frequency at a distribution outlet and timestamp it using a clock which is synchronized to other clocks using a synchronization method known as network time protocol. Network time, this kind of synchronization method will kind of have synchronization accuracies of a few milliseconds, and this is usually acceptable for the study of the electromechanical phenomena like swings, loss of synchronism, etc., which I had mentioned some time ago. Now, the typical scheme which is used is that you have got a frequency measurement device which could actually convey the measurement, time stamp it. Now, the time stamping is done based on connection to a network time protocol server, and all these computers here could be synchronized to the pool of network time protocol servers. So, all the clocks on these computers are synchronized. So, they will be used to timestamp the frequency measurements, and these frequency measurements then are conveyed, synchronized frequency are conveyed to a central server which in fact collates the measurements, and then they are available for study. So, this is an example of a wide area system. In fact, this was implemented at IIT Bombay, and we in fact at various points of time we in fact had these installed at various places. Okay. Now, a practical or commercial wide area measurement system would use in fact GPS satellites to give a much GPS is global positioning system satellites, the same thing which is used to pinpoint your location on your mobile phone and so on. So, this kind of these GPS satellites in fact give synchronization signals, but the synchronization error in case of GPS based time synchronization is much smaller, is of the order of a few microseconds or less in fact, and this PMUs, the phasor measurement units, measure not only frequency, but actually sample the voltages and compute the phasor. Okay. So, voltage phasor. How is the voltage phasor computed? Essentially the Fourier component, the cosine and sine component of the sinusoidal waveform, the fundamental frequency component is actually computed by the PMU. The PMU in fact uses this DFT algorithm. In one of our tutorial sheets, we have given a example or an exercise for you to actually compute the DFT of a waveform, and this in fact gives you the Fourier series components, which will give you the magnitude and angle of the voltage, the phasor as seen at this bus. But since all these phasor measurement units which are using DFT to compute these magnitudes and angles of the fundamental component of the sinusoidal waveforms are time synchronized, what you can do is actually compare the phasor. So, since you have got the synchronization accuracy of a microsecond or less, your phase angle also can be compared, because if of course there is no time synchronization, phase angle of a phasor does not make any sense. Okay, you should have a common time axis, then only we can in fact talk of phase angular differences. So, in fact if you have got good synchronization accuracy as is obtained with GPS satellites, it is possible in fact to use these PMUs using this highly accurate time stamping to compute the phase angular differences as well. So, you can in fact with 1 microsecond accuracy you can get 0.018 degree, the errors less than 0.018 degree between the relative angles between various PMUs. So, that is a very fairly high degree of accuracy, and because of that you can actually measure these phasors, and these are all time synchronized phasors, and these can be sent to a load dispatch center. So, this is a practical wide area measurement scheme which is in fact being implemented in our country, and it is very useful in a synchronous grid. In fact, there is a project being completed in India. It is in fact phase 1 is completed, where more than 1,000 such phasor measurement units have been put at various substations, generators, and all this data has been collated in using PDCs, which are phasor data concentrators, which actually receive all this data, collate them, store them, pass it on for some analytical use. So, in fact, a few more PMUs are also being installed as a part of phase 2, and every line is being monitored by PMUs or phasor measurement units at both ends. So, we can in fact use these measurements for not only post facto analysis, but also use them for possibly for monitoring and even for real time control, although there are not many applications yet, but it is certainly conceivable. Yeah. So, this is essentially how this whole system is architecture is, and you have got PMUs which in fact through the routers have sent it to a hierarchical system of phasor data concentrators, where all the data is collated and passed on to other analytical functions or to other phasor data concentrators higher in the hierarchy. Now, this kind of system is a practical system which is being implemented in India. So, with this we can in fact have real life measurements, and I am going to show you a few examples of such real life measurements which have been monitored over the past several years. This is in 2011 snapshot of a generator trip, and as you see that the frequencies at various points, you will find that there is a swing as I mentioned, and also there is a overall drop in the center of inertia motion. Yes. In fact, because we were monitoring these measurements over quite a bit of time, what we find is that from 2011 to 2015, there has actually been a change in the characteristic of the grid. You will find that in fact here, if you look at it, the frequency drop for a 1000 megawatt trip which took place in 2011 is about 0.225 hertz, slightly more than that, and whereas in 2015 it is only 0.13 hertz. So, you find that also the slope of this characteristic, that is the initial rate of drop of frequency when there is a sudden load generation imbalance is which is dependent only on the overall inertia of the system, okay, the rotating inertia. So, if there is a sudden change in the load generation imbalance, you would expect of course the frequency, center of inertia frequency to fall, and the rate of change of center of inertia frequency is dependent or inversely proportional to the total inertia of the rotating masses in the system. And you see that this inertia in fact is much higher in 2015 because our grid has grown. There are a lot of generators which in fact have been connected to the grid, and therefore the rate of changes has in fact changed. The steady state settling frequency for 1000 megawatt tripping in 2011 and 15 is also different. You will find that because the number of loads have increased and each load has got a load generation load frequency dependence. You also have governor action, and because of that you find that in 2015 for the same 1000 megawatt tripping, you will find that there has been much lower frequency drop, steady state frequency drop than in 2011. In fact, most recently we find a further similar behavior, and one of the differences which we see in 2015 and 2019 is that you have got, whereas here it is more or less like a exponential kind of drop, 1 minus e raised to minus t by tau kind of like an RL circuit kind of drop. Here you see a kind of second order response, which is probably because of the control systems like governors, which are now more active. In 2011 not all governing systems were active, but now the new grid code is in fact requires governors to be active. So, you see a kind of second order response also, that is you see a kind of a slightly different from the just a simple plain kind of e raised to minus t by tau kind of response. Okay. So, this kind of differences you do see because of these measurements, but what is most important is that in steady state the machines stay in synchronism. In fact, after a disturbance there are swings, but if there is a load generation balance as well, you will find that there is a change in the center of inertia motion, that is the frequency also changes of the entire system. Of course, their machines are still in synchronism because all the frequencies are still equal. Okay. We also have observed other phenomenon in synchronous grids which are like loss of synchronism. Loss of synchronism is not an acceptable kind of situation. In a loss of synchronism situation, the synchronous machines are connected to each other, but the restorative forces are no longer keeping the machines together in synchronism. So, you will find that the synchronous machines tend to fly apart, and this kind of thing has happened in the past. Now, normally if you have got two synchronous machines connected together by AC transmission, you cannot have them operating at different frequencies. Just let us as a thought experiment consider two synchronous sources connected by by AC transmission path of reactance X, and suppose one of the sources at 50 hertz and the other at 51 hertz. One of the things you will find is that under such a situation, the power flow in the line in fact keeps going from positive to negative. In fact, the power flow, three phase power flow, which is normally constant in sinusoidal steady state, in case you have got two voltage sources with different frequencies, you can consider one as a voltage, take it as a reference phasor, then the other phasor is continuously rotating. Because it is continuously rotating with respect to the first phasor, the phase angular difference at the two ends is continuously changing from 0 to 180 to 360 and so on. And therefore, the power flow in fact keeps changing up and down. And if you in fact look at the midpoint voltage here, it is also kind of it is a 50 hertz system, but because there are frequency, one is at 50 and other is at 51, the voltage in the midpoint in fact shows beats. So, you can't operate this way, because that would mean your voltage magnitudes would keep on fluctuating, power flows would be changing. In fact, if power flows are changing, that would mean the torques on the machine also will be fluctuating quite wildly. This will damage in fact the equipment. The voltage also will be fluctuating also in a wild manner, and therefore, you would need to trip. In fact, it turns out that because the voltage at the midpoint kind of because these beats can become 0 under this situation, relays which are distance relays may in fact think that this is a fault, and they trip, and because of that these two systems in fact undergo a natural separation. So, in case loss of synchronism occurs and at some point in the transmission system the voltages in fact oscillate the way I have shown you here, then usually some relays pick it up and trip, inadvertent, means it is not intentional, but they trip and the system separates into two parts, which is just as well, because you can't operate this way. Okay. This is of course only a thought experiment where 50 hertz machine of 50 hertz is connected to another machine at 51 hertz, and we just solve this circuit. But in real life, for example, this is a a laboratory experiment which was carried out by Dr. Shubhanga of NIT Surathkal, and you find that he deliberately tried to make a synchronous machine fall out of synchronism. This machine in fact was made to fall out of synchronism by gradually increasing the stretch, that is delta 1 minus delta 2 between the two machines is you may go on making it increase. After some point of time, the machines, the transmission link between the two machines cannot restore it, because the restoring force is a function of sine delta 1 minus delta 2, and sine delta 1 minus delta 2 in fact can even reverse in sign. So, this was in fact an experiment done in the laboratory where a synchronous machine was connected to the grid. A synchronous machine in the laboratory was connected to the grid. The grid can be considered as a large synchronous machine. So, there were two machines connected to each other, and the machines lose synchronism. And if you look at the waveforms of the voltage and the currents, they are in fact exactly what, not exactly of course, rather I would say very familiarly is very similar to the voltage and waveforms from this theoretical example of two voltage sources connected by a transmission line. So, you do see that there is a kind of a system separation. This is called system separation in a synchronous grid. In fact, such system separations are quite rare, but they have in fact occurred in practice. Now, once this kind of situation occurs, you need to separate out the machines which have lost synchronism with respect to the other. So, you need to kind of island them. If you do not island them, usually some relays will pick up and think it is some fault or some equipment failure, and they will in fact trip out, and then you have an uncontrolled separation. So, either you have to trip it or the relays will trip it out. So, this kind of thing happens. In fact, it has happened in the past. You see similar signatures for voltages. These are the voltages for a thing for a disturbance which occurred more than a decade back in western India. You also have in 2012 there was a blackout, and there too the system lost synchronism. So, in two parts of the system in fact the frequencies, the system split apart, that is it could not pull back into synchronism. So, this is something which occurs in a synchronous grid. This is actually the measurements taken by phasor measurement units which were present in the grid. These are by the simple frequency measurement system which is synchronized using NTP network time protocol, and this is the commercial system or the actual system measurements, rather the measurements taken by a practical wide area measurement system. So, you see this loss of synchronism occurring in this system, and in fact, the entire North India, which consists of large number of synchronous machines, separated from the rest of the system. Now, once you one important thing is that once you separate two systems, although initially the total load and the generation may be balanced, once the two systems separate out, the load and generation balance in individual synchronous grids. So, there are two now synchronous grids. In case the electrical connections between the two parts of the grid are broken, then you actually have two separate synchronous grids. And now within the synchronous grid, two synchronous grids, you have to maintain load generation balance. Otherwise, the center of inertia frequency in each individual grid will in fact not be stable. It will either fall down precipitously or increase. In fact, if you have got load generation balance and you separate out into two islands, one of the islands could be under generated, in which case the other one would be having excess generation, because before this disturbance they were balanced. So, once you separate out, they may not be balanced, and there can be a sudden change in frequency, and a sudden change in frequency which is not arrested quickly usually leads to a complete blackout. That happens because if the frequency falls below 47, it said many of the thermal steam turbine generators, they in fact trip out, or if the frequency goes above 51 hertz or so, or 52 hertz, they will trip out on overspeeding. So, both at under frequency and over frequency, the generators trip out. The under frequency, one of the reasons that below 47 usually you have got larger blade vibrations in a turbine, because the resonant frequencies of the blades get excited in case the frequency falls below 47. So, you have in fact many thermal generators will actually trip, and this is what happened in the 2012 blackout. You had a system which was integrated, a certain disturbance caused the phase angular difference between the two parts of the grid to go on increasing. After a point, the separation was so much that the machines could not be brought back. Under normal circumstances, you have a swing where there is a increase in the phase angular difference between two parts of the grid, but the transmission lines are able to restore it because of the spring like action. But if the spring loses its springiness, then you have a situation where you lose synchronous, and this is because the spring is non-linear. Okay, if you stretch it too much, it loses its stiffness. So, this is what we saw. In fact, on the very next day there was another blackout, but the pattern was somewhat different. Now, it is not very easy in a nonlinear grid in a system with many transmission lines to actually predict how the cut set or the separation will occur. So, so what we discussed today was one of the disturbances or one of the phenomena which we see in a synchronous grids. In the next lecture, we will see another phenomena called unstable power swings, which is highlighted in the figure shown here, and we shall also move on to see how an asynchronous grid is behaves, and also how a large power grid is operated. With this, we stop today's lecture.